here we're going to talk about directly how the FIB damages the sample. And I want to say a quick thank you to Mark Nigerian of Thermo Fisher, who gave us this wonderful paper by Giannuzzi, Gertz, and Ringnold. These kind of show how the gallium ions that we talked about that are either embedded in the sample or even the interstitial atoms and how they affect the TEM image. So in this top row, we're looking at a cross-sectional view of the lamella. So lamella goes through a thinning process, and then someone takes a cross-section of that and looks at it in the TEM. So in 1A, you're looking at amorphous layer damage, which is this fuzzy layer that's caused by 30 kV gallium ion beam. And you can see that this thickness is about 20-ish nanometers thick. And this corresponds to a very irregular view, a very blurry view. And that's because when you're talking about electron scattering with all these materials or interstitial atoms, electrons are going to scatter and it's not going to give you really high quality. The other thing you need to keep in mind is that the thinner you go in terms of lamella, the more or the less good material you'll have. For instance, if you're looking at an 80 nanometer lamella, but you only used a 30 kV gallium ion beam on both sides, you're going to have 30 nanometers on the front face of the lamella of damaged layer and 30 nanometers on the back, meaning that 60 nanometers of your 80 nanometer thick lamella is damaged. You only have 20 nanometers of good material to image. So you're going to get a really terrible image quality. The way you go about this is using lower lining energies for your FIB. So you drop it down to 5 kV, and this is kind of what's referred to as polishing, where you're mainly getting rid of this damaged layer. So in 1B, you see that this damaged layer is significantly less than using a 30 kV beam. And this damaged layer is about 6 or so nanometers thick. And you can see the corresponding TEM image when it's polished with this lower one. So you see the atom starting to take shape, not as much damage, layer that's going on, just a better resolution. And this process just repeats and repeats. So even you drop your energy even lower to 2 kV. And here you can see the damaged layer is this fuzzy layer right here. It's about 3 nanometers thick and so on. So it's almost close to a 1-to-1 ratio of damaged layer to whatever FIB energy you're using. Some FIBs nowadays could go as low as a few hundred volts. So you get even better image quality. So this is a very important thing to keep in mind as you're thinning your lamella. Another thing you can get is redeposition. And so when we talked about how it's not just the tip of the FIB that's milling the material, but it's also the tail ends or the sides of the beam. You're not actually thinning the window itself, but you're actually milling the surrounding material. And so this material can sometimes reattach itself to the face of the lamella. And that's what you see here in this left image. You see all these, looks like bubbles in the TEM, but this is actually redeposited material going onto the face. And so when you look at a higher res image, you can see a lot of variation in grayscale and thickness. And you can see how the resolution changes from, say, in this top right versus this bottom left. So this is something you really have to keep in mind, which is why you really need to pay attention to what materials you're milling, the shape of your beam, over tilt, box placement. And this is how it kind of starts taking form of an art form.